I'm Richard Anderson. 75 years ago, the ground I'm standing on was productive farmland. After just 3 generations of farming, the rich black topsoil that covered this ground for thousands of years has vanished like so much dust in the wind. From the very first time the prairie sod was broken up and turned over, the natural cycle of soil creation was interrupted. The land was not so much farmed as it was mined. Each year, more topsoil disappeared than was created. But this is not the story of the failure of a single farm, or of one region's failure to manage its soil resource. Across the globe, the world's agriculture faces a growing crisis. The 4 greatest food-producing countries, the United States, the USSR, China, and India, are losing topsoil at the rate of 13.2 billion tons a year. The Soviet Union probably leads the world in soil loss. While still a member of the Politburo, Mikhail Gorbachev urged Soviet planters to heed the warnings of Russia's soil scientists. Winds sweeping across northern China now carry away so much topsoil that scientists at observatories in Mauna Loa, Hawaii, can tell when spring plowing starts in North China. India now estimates that 60% of its cropland is eroding excessively. Sediment from soil erosion is the single greatest pollutant of the world's lakes and streams. Scientists studying sediment samples estimate that soil carried to the ocean has increased from 9 billion tons a year before man began to cultivate the land to over 27 billion tons today. Multi-purpose dams, often the centerpieces of third world development strategies, are filling up with sediments at rates never dreamed of by their planters. The Magla Reservoir in Pakistan will be filled 25 years sooner than expected. In Africa, the death of the soil has become pandemic. Millions of people have been forced to leave land that will no longer feed them. The specter of the African experience is now haunting the very heartland of America. 200 million acres are undergoing severe desertification. Almost half of all U.S. cropland is losing topsoil at a rate faster than it is created. Hunger has often been seen merely as a problem of distribution. But the growth in population will soon overtake our food-producing capability. Even if the planet's food production could be evenly distributed, it is estimated that by the year 2000, the world's agriculture will have to increase production by 26%. 56% by the year 2020. We have been taught to believe that agriculture will continue to keep finding ways to be ever more productive. But the rate at which world agricultural productivity increases has begun to flatten. In many areas, productivity has actually begun to drop. Each year, the total number of acres available for cultivation gets smaller. In the next few minutes, we'll be examining this problem and the global search for solutions. But first, let's look at how topsoil, that most precious of resources, works. Since the beginning of time, the complex forces of nature have been working to turn rock into soil. Yet in all that time, precious little has been produced. Arable land covers just 4% of the Earth's surface. In most places, just 6 inches of fertile topsoil separates us from the desolation below. In its natural state, soil is far more than simply the ground beneath our feet. Near the surface, microscopic organisms reduce plant materials such as roots, stalks, and leaves to a nutrient-rich layer of dark tilth. Small animals like earthworms tunnel beneath the surface, producing tiny channels which make water and minerals available and provide essential pathways to the subsoil for new rootlets. The surface blanket of organic matter provides shade, holding in moisture and allowing the soil to breathe. The ground below is protected from the force of raindrops that might otherwise compact the surface and prevent the water from being absorbed by the layers below. The topsoil is a great self-sustaining engine, producing an abundance of the necessary stuff of life, and in the process, constantly revitalizing itself. When man first began to plant seeds, he utilized the natural structure of the topsoil to grow his crops. He simply poked a hole in the surface with a stick, inserted the seed, and closed the opening with his foot. Without realizing it, he had placed his seed in a near-perfect environment. The topsoil provided near-constant humidity, with a continuous supply of nutrients from above and minerals from below, even if there was little rain. In 1701, Jethro Tull, an English agriculturist, developed the first mechanized seed drill, placing the seed in furrowed rows. Since Tull believed that plants grew by absorbing tiny particles of earth, he recommended pulverizing the ground so that the plants could be better nurtured. Although Tull's theories about the benefits to plants of pulverizing the soil were fundamentally incorrect, they gained universal acceptance and became the underlying premise of the mechanized farming practices that continue to dominate the world's agriculture. About the same time that Tull was urging farmers to obliterate the structure of their topsoil, the first moldboard plow was developed in Europe. The invention was later perfected in the United States by no less an American than Thomas Jefferson. The implement was cast in iron and, like earlier plows, was dragged along as it sliced through the ground. The new device, however, featured a molded side that curved gracefully to raise the furrow and turn it over. By 1850, the John Deere Company was shipping 1,600 steel plows a year. A single man with a team could zip through the previously unplowable prairie sods to expose the deep, rich bottomland soils of America's heartland. All over the world, the ranges and grasslands were put to the plow. The planet's ability to feed itself doubled and redoubled over and over again. But even as the new farms of the Midwest were springing up, the first signs that something was wrong with this magnificent new agriculture could already be seen. The farms of Vermont, once the breadbasket of the colonies, were going bust. The land played out. Today, Vermont farmhouses, abandoned nearly 200 years ago, sit among forest trees that were once farmers' fields. The age of mechanized farming had brought instability to the farm. Where once it had been common for generation after generation to work the same piece of land, farmers became like miners, taking from the soil its vast riches, then moving on to the next mother lode once their land had run out. By the 1930s, dust bowls sent wave after wave of farmers from land turned to dust after just 100 years of cultivation. The soil conservation movement of the 40s brought practices such as contour plowing, windbreaks, flood channels, and sediment dams to farmers' fields. Burgeoning foreign markets brought good prices, while advances in seed, fertilizer, pesticides, and herbicides masked the ongoing depletion of the soil with ever greater crop yield. In fact, the loss of the world's topsoil has been steadily accelerating. After a crop is harvested, the ground is plowed and readied for the next planting. The land is worked and reworked until it is nearly pulverized and largely devoid of organic surface residue. When the rains come, the force of the drops will compact the surface, lowering the absorption rate. Since the tilling processes unhinged the mechanical bonds that held the soil together, the resulting runoff will carry it away. When the rains stop, the lack of a surface cover will allow what little moisture was absorbed to quickly evaporate, exposing the dry soil to the ravages of wind. The loss of the top layer of organic material will also mean that the natural processes that provide nutrients to the soil no longer function. Below the surface, the capillary system has been destroyed, halting the delivery of moisture from above and minerals from below.
In the case of shallow soils, as the topsoil is lost, the soil becomes too thin and eventually the land would be abandoned. But this is not the likely case for much of our croplands actually have fairly deep subsoils. So as the topsoil is lost, more and more subsoil is worked into the tillage layer where the crops are sown. And in order for the farmer to maintain his yield levels, what he has done is he has increased the amount of fertilizer chemical fertilizers in order to provide adequate nutrients to the crop. And also, he has to apply more fuel for his tractors because the soils are more difficult to work and to cultivate.
But the decline in soil productivity has meant that the cost to produce a given yield keeps going up. Greater and greater economies of scale are needed to make a profit. Fewer and fewer farmers are using larger and larger tractors to plow bigger and bigger fields. The windbreaks have come down. The flood channels between fields have been eliminated, and the huge tractors can't negotiate the twists and turns of contour plowing. The United States farm policies of the 80s have sought to take marginal land out of production and stabilize farm prices by paying farmers not to plant a portion of their land. The 1985 Farm Bill requires that extensive soil conservation plans be in place before farmers can receive 1990 Farm Program payments. But once again, the farmer is caught in the middle. Recent U.S. studies have concluded that if farmers were to invest in appropriate erosion controls, their profit margins would disappear entirely. Today's farmer can't just pick up and move to new land for a fresh start. The economic consequences of the U.S. farm crisis are already far-reaching. Displaced farmers fill unemployment roles. Unpaid farm debt has to be absorbed by the rest of the economy. Farm subsidies have become a huge obstacle in efforts to balance the federal budget. Since agricultural products are our greatest export, the health of the farm economy directly impacts the balance of trade deficit. By the 1970s, a number of farmers started to search for a better way. The movement they started has come to be known as conservation tillage. Motivated initially by the high cost of fuel, they sought to reduce the number of times a field was tilled before planting, breaking up the soil to a lesser degree and leaving a higher amount of crop residue on the surface. The techniques vary from simply reducing the amount of tillage to eliminating plowing altogether. The USDA, which considers conservation tillage any method that leaves at least 30% of the crop residue on the surface, has been studying various reduced tillage techniques and encouraging farmers to convert to the practice. But while conservation farming has become the acknowledged future of agriculture, mastery of the technology necessary to convert to the practice has been elusive. Getting seed into ground that has a high amount of surface residue presents special problems.
Well, the problem with a lot of the earlier equipment, much of which was experimental, was that the equipment was not designed to handle heavy surface residues. Oftentimes the equipment was too heavy, and another limitation of getting it on the farm was that it was too expensive.
But the size and expense of equipment did not concern farmers nearly as much as something else: inconsistent emergence. Quite simply, the crops did not always emerge from the soil. Farmers were being asked to convert to a practice with a higher degree of short-term risk for the long-term advantage of conservation. Emergence problems are not exclusive to conservation tillage. A great deal of agricultural research over the years has been directed toward finding a solution to this problem. Most of the emphasis in the United States has focused on seed and fertilizers, but scientists at New Zealand's Massey University took a different approach. Alerted to the problems of conservation tillage emergence in 1967, they began a study of the relationship between seed environment and emergence that continues today. Using a unique process, large bins of actual soil were removed intact from fields so that they could be subjected to various climatic and tillage conditions. Prototypes of various openers were built, and the variations on crop emergence were then studied. It was during the course of one such study that researchers made a startling discovery. The director of the project is John Baker.
Well, there's been a situation in Australia where seeds had been sown into an untilled soil at the same depth with two different openers, and there was a markedly different emergence pattern. So we set about developing a program that would attempt to identify any relationship between the emergence of seeds and the shape of the slot. The simple hoe-type opener creates a U-shape of slot with a wide base. The double disc opener, in contrast, creates quite a neat V shape with straight walls. We felt that the straight walls were impeding germination and root growth, so we sought to take away that V shape and invert it more or less so it was narrow at the top and wide at the bottom instead of the other way round. So what we came up with was the inverted T shape with a narrow slit here and a wide base here for the seed to sit on. We'd planted side-by-side rows of barley as a comparison between the three openers. In dry soils, the results were quite spectacular. We got something like 3 times the amount of emergence out of the inverted T opener compared with the other two. Since then, we've repeated the experiment many times, and the results have been even more spectacular.
Test after test with various crops and soil conditions dramatically demonstrated the superiority of the new cross-slot opening. Even in a field study of soil, with a moisture level close to the permanent wilting point, a moisture level at which plants theoretically cannot grow, the cross-slot planting had a 50% emergence rate. No seedling at all emerged in plots using conventional openers. The Massey University group knew they had made a major breakthrough, but ironically, they didn't know why it worked so well. Later studies concentrated on finding out why the new opener was so effective.
It turns out that with traditional openers, there are 2 major problems. With the double disc type opener, residue is pushed down into the slot and the seed sits on top of this residue, and when the residue is wet and decays, that affects the seed germination. When it's dry, it allows moisture vapor to escape through the residue and out of the slot. With the inverted T-type opener, the slot is actually created from the bottom up, so the residue is never pushed down into the slot in the first place, and when the top is sealed down, it effectively traps the moisture so it's not lost from the slot itself. The result is that the seed and the fertilizer are placed separately in the slot in a near-perfect environment with minimal disturbance to the soil structure.
The device the researchers created